What? Well, those are yours. Those are yours. So a lot of them are yours. Take them. Review. Now, I know that you guys hear that and you get all mad about it, but largely review. There's not a whole lot of new material when it comes to talking about collisions. So in dealing with what I need you to know for collisions, let's start with the most simple of examples, just a standard, perfectly inelastic collision. And in an inelastic collision, you should recall that kinetic energy is not conserved. That's the definition of an inelastic collision. That kinetic energy is not conserved. I want to be really careful here because I gave a retake this morning to a lot of AP Physics C students. And what gets you guys tends to be the details. You tend to not pay attention close enough to details. And in a test situation, especially this morning, you have to understand there was only 10 questions on the multiple choice test I gave this morning, but students who got here early had 40 minutes to work on a 10-question test. So they had more than enough time. When you look at the grand scheme, you guys took a test this morning, that could have been enough time for a full 35-question test, and you had 10. So with all of that deep reading you did and that care that you took to answer every question carefully and reread it and make sure and check, you get none of that. In the actual exam, you get less than half that amount of time per question. Now, it's a retake. I'm trying to help your grades go up. But when it comes to working the problems, I was talking to Hannah about this yesterday. When it comes to the exam, you're going to have to start learning which questions you're good at and which questions you're not. And focus on the ones you're good at because you don't have enough time for all of them. Now, it's still, like I said, it's still early in the year. You still have a lot of time. A lot of your skill set on multiple choice like that's going to improve. But it's details that you tend to miss. And those details need to be improved upon. It's the difference between asking questions like, how much energy is lost versus what is the change of energy versus what is the percentage of energy lost. These subtle little differences all produce a different answer on the test. Similar with impulse and momentum. We tend to lose the details. The word inelastic means that kinetic energy is not conserved, but momentum is conserved. It's conserved in almost any interaction. Now, in this example that we're doing right now, we'll make one of the cars moving at 10 meters per second, the other car moving at 5 meters per second. And let's make this car 200 kilograms and this car 100 kilograms. And let's say that this collision is actually perfectly inelastic. Perfectly inelastic is a sign to you that the two objects are going to stick together. They might use the word couple if we're talking about train cars during the course of the collision. They don't have to say any of that. All they have to say is that it is a perfectly inelastic collision. And that has to mean to you that they will basically have the same velocity after the collision. So, in setting up one of these questions, I tend to do it the same way every time with a before and after. And this blue line in the middle represents where the collision took place. I tend to draw above the top of that a direction that I will call positive so that I don't forget that momentum is a vector quantity. Now, again, Momentum for the 200 kilogram car plus momentum for the 100 kilogram car represents the total momentum of the system. This has to be equal to the momentum of the 200 kilogram car plus the momentum of the 100 kilogram car after the collision. These objects still exist after the collision, so they may have momentum. I need to ensure that I take into account all the momentum of the system both before and after the collision. Now, since momentum is conserved, the total momentum before the collision must equal the total momentum after. It's a vector quantity, so I need to be aware of direction. Now, this first example, I didn't mess around too much with that idea. I made all the directions the same to ensure I can get a reasonably straightforward answer. Now, this is going to be 2,500 kilograms meters per second, and it represents the momentum of the system. Right? That's the total momentum of the system. And although I know it will have to be equal to the momentum after the collision, it's important to understand that if you're asked for the momentum of the system, this is the answer. And there's no reason why they couldn't ask that question. Now afterwards, since I know it's perfectly inelastic, I tend to put the masses together and treat it as if it's one object, which is true since they have the same velocity. Now, finding the velocity is relatively straightforward in this case, 25 thirds, or approximately 8 1/3 meters per second. Now, this is a very straightforward example, but believe it or not, this is the most common question on the AP Physics C exam when it comes to linear momentum collisions. One object strikes another, they stick together. It's going to be part C out of part F. They don't have generally questions that are entirely about momentum. They just don't. I'm sure I can find one or two throughout the literature, which I'll be looking for your exam. But ultimately, collisions conserve momentum. That's what it comes down to. Now, in this particular example, there are a couple things I want you to think about that are kind of down the road questions. Things that I would look at asking you should this be an actual test. For example, although you found this answer, I would probably ask as a follow-up, say part B of the question, for you to discuss with me the impulse of each object. It might not be obvious to you, but the net impulse for the system has to be 0. I wouldn't expect you to come to that conclusion on your own, but if the momentum of the system doesn't change, and impulse is change in momentum, then the impulse has to be 0 for the system. Everybody follow that line of reasoning? That was if A equals B and B equals C, then A equals C. That's what it comes right down to. Now, be very careful here because you guys have calculus. In the long term, what this actually means is for the system, dp dt equals 0. I'm saying that because we could get some expression for the momentum of the system. And if we know that it's a collision, then the derivative of that expression would have to be 0 through a collision. It doesn't seem obvious, but these are all those little pieces that I'm noticing tend to get left. I don't know if this will be on the exam, but they could ask it. It's in the textbook. So I would have probably written it as dp equals 0, or I'm sorry, delta p equals 0, because that's how we frame impulse. Now, that doesn't stop you from asking questions like, what is the impulse experienced by car number 1? Or what is the impulse experienced by car number 2? it should be pretty straightforward that the impulse experienced by one car will be equal and opposite to the impulse experienced by the other. The cars will have individual impulses, but the net impulse of the system will be 0. Oh, that's not going to work. So I don't have a whole lot of room here. I'll just go to another page. Why not? Consider the 200 kilogram car. The 200 kilogram car had a final velocity of 8.3 meters per second, but it had an initial velocity of 10 meters per second. It was 200 kilograms. So the change in momentum of this car would have been 200 times 8.3 minus 10. That's 1 2/3, right? Negative 1 2/3. All right, I'll do it another way, but I'll get the same result. Why don't you guys do part of this? Do a little heavy lifting. What is 8 1/3 minus 10? And if you need your calculator, I'm really, really sad for you. I'm not waiting. It's 1 2/3. So 200 times 1 2/3, which is negative 4/3. Looks to me like it's negative 800 thirds, which is, I don't know. I don't know what that change of momentum is. I'm going to leave it as 800 thirds. I'm not scared of fractions, and it doesn't bother me that that's the change of momentum of the 200 kilogram car. Now, consider the 100 kilogram car. And I'm just doing this so that you guys understand that I expect you guys to know this, but I expect you can prove it as well. The final velocity, yes, go ahead.
You said negative 2/3, but you wrote negative 4/3, and I just got a difference.
I said negative 1 2/3,
So,
which is negative. It's not negative 4/3. You're right. Thank you. Thank you. It is December 10th at, what is that, 10:47? Shelton made a mistake in arithmetic. 1 2/3 is not 4/3. It's 5/3. So that's negative 5/3. And that would make this not negative 800, but negative 1,000 thirds. If
negative 340.
what?
I got negative 340.
Okay. I think I'm okay with this.
But I just don't get it.
What? That's 333.
Divided by 3? Okay, yeah, that's close.
It's not close. It's exactly. 8.3 is an estimate. It was 25 thirds, right? So it's 8.3 repeating. So negative 1,000 thirds is perfect.
Okay.
No problems with my decimals. I just can't add. All right, keeping on with this. 8.3 for this one. The initial velocity was 5. So my 100 kilogram car had a change in momentum equal to 100 times the change in velocity, which is 8.3 minus 5. All right? Well, that's 3.3 or 10 thirds. So 100 times 10 thirds, which is 1,000 thirds. It has to be exactly the opposite. I really didn't have to do any of that work. If I had confidence in this answer, I knew that the change of momentum of the other car had to be positive 1,000 thirds. Now, this is just a follow-up to the actual collision. And there's lots of other things here, too. If we know that the collision lasted for about point whatever seconds, you can figure out how much force each car experienced. Be aware that this doesn't change the fact that this must have occurred because a net force acted on the car during the course of that collision. I would expect that all of these are excellent follow-up questions. Moreover, we did not do all that work on energy to throw that out. I think a perfectly great follow-up to this would also be to ask you about the energy of the system. There's lots of ways this question can go. There's things like how much energy was lost. They probably won't say that. They'll probably say how much energy is converted to some other form. They might ask what percentage, what is the ratio, what is the amount of energy in the beginning compared to the amount of energy at the end. Who knows how they're going to ask it? You need to recognize that both cars had kinetic energy before the collision, and that their combined motion after the collision also has kinetic energy. It's incumbent upon you to recognize that these are not going to be equal for an inelastic collision. But it is clear that you should understand how to manipulate this. The amount of energy missing would be to take this number and subtract it from this number. Do you know how many times we've had a test in here when you've asked, did you guys just subtract those two numbers? Yeah. It asked how much was missing, what was different. Difference is the delta. You're going to subtract. I suspect that you're often distracted by that. And even now, if I start putting the numbers in, you'll get more distracted with the fact that there's numbers here than what we're actually doing. This represents the amount of energy in the system before. This represents the energy in the system after. What's not represented here is how much energy was transferred into another form. It's your job to recognize that the missing energy is what was taken out of the system. I need you guys to be on the ball enough for me not to have to spell it out like that, but you need me to. So write that in your notes, that if you're asked how much energy is missing, you're going to subtract the final energy from the initial energy. That if you're asked a more complicated question, like what is the percentage of energy that is missing, that you would recognize how to calculate the percentage, the percent difference. And if you don't, it would be delta KE divided by KE initial. That's the percentage of energy that's missing. They might go further. They might give you the ratio of the kinetic energy lost to the kinetic energy initial and ask you how fast it was going after the collision. They can work this problem backwards and tell you the amount of energy lost. Just be prepared to discuss the energy that is left in the system after a collision. All right, let's go do another example. This next example I'm doing just because I want to prove something to you, but I don't want to spend a lot of time on this particular example. Again, yeah, you should probably calculate it, but that requires you guys to have the old calculators out. Let's do the bullet and block equation. There's lots of ways this can go. Let's start with the more basic one. The bullet strikes a block. That's the basic part of the collision. The bullet, though, can do a number of things here, depending on what we have for a block. There is the possibility that the bullet becomes lodged in the block. That would be a perfectly inelastic collision. Those are the easiest ones for test writers to write. However, it's just as possible the bullet could pass through the block, imbuing the block with a certain amount of momentum, but slowing the bullet down. I want to talk about these for just a minute because they represent the least interesting question. And it doesn't have to penetrate the block. It could bounce off the block too. It's the same kind of question. What I want you to understand is that in this question there's MV for the bullet and MV for the block. Assuming the block isn't moving, this is pretty easy. The problem is that afterwards there's MV for the block and MV for the bullet. Now we can assume all sorts of stuff, like they might give us the mass of the block and the mass of the bullet. They might give us the velocity of the bullet just before it strikes the block. They might tell us that the block isn't moving. Pretty common. The issue here is that after the collision, there are two unknowns. And no matter what, momentum can't answer a question that has two unknowns. The issue comes down to conservation of momentum only generates one equation, which means it can only solve for one unknown. So if you're given a question like this and you feel like there's an unknown there's no way to solve it, there has got to be some other information in the problem, something you're missing. Hold on, there's only so much that can be done with conservation of momentum. That's why they talk about perfectly inelastic collisions, because it makes these two the same number and they have to do less work. If I want to give this to you as an actual problem, I have to have already told myself or figured out how fast the bullet's going. Make up some number so that you have some way of solving for the other velocity of the block. That's why these are not very often in the literature. Now, they do other things in the literature that do make this a little bit more complicated, which is what I do want to show you. They won't ask this question on your exam. This is an AP Physics 1 question. What they will do is they might take this out of the way. And place both of these on like a rope, or place this one like on a rope, so that when the bullet strikes the block, this will swing upwards while the bullet travels away. This is the kind of combined problem you should expect on your test. This particular one is called a ballistic pendulum. And this represents your first FRQ style question that I would really like to go over, since this is really what you should be expected to do. So in order to start the problem cleanly, we have a bullet that's going to strike a block. The block is hanging on a rope that is 1.5 meters long. The block has a mass of 500 grams. And the bullet has a mass of 20 grams. Okay, this is problem type number 1. The bullet becomes embedded in the block. And the block and bullet swing upwards. An angle of 30 degrees. What is the initial velocity of the bullet? This is a pretty typical question on the AP exam. The difference is on the AP exam, it won't be a block. It'll probably be an object with extension, so you'll have to use angular momentum, not linear momentum. But questions like this is where we are now, so we have to understand the conservation momentum concept as it applies to this problem. Hold on. I got many things going on at once. So to actually solve this problem, you need to know when energy is conserved versus when momentum is conserved. Momentum is only conserved during the collision. That collision represents the instantaneous moment before the bullet strikes the block and the instantaneous moment after the bullet strikes the block. There are actually 3 things happening in this problem. Momentum is conserved from here to here. That's the collision. After this collision, the box and the block have some velocity. An unknown velocity, by the way. Energy is conserved from here to here. There's an interaction between the block and the bullet and the earth. As it's swinging upwards, it's converting kinetic energy into potential energy. It's incumbent upon you to know the difference, to be able to predict when you're supposed to use conservation of energy versus conservation of momentum. This is your test. Something like this. And I'll tell you the easy way to figure it out. If an object's height is changing, it's likely conservation of energy. And if an object strikes another object, it's likely conservation of momentum. There is no object striking another object from here to here. It is a single object that's changing height. On the other hand, no object changed height over here. The height remained the same for all the objects, but the bullet came into contact with the block. That's the collision. Now, to actually operate this question, you have to figure out which part of the problem to solve first. It might not be obvious for a first timer, so let's take a look. We have mass of the bullet. We have the velocity initial of the bullet plus mass of the block, which I'll just put W here for a wooden block, times the velocity of the block before the collision, clearly 0. And that's going to have to equal the mass of the bullet plus the mass of the block times their combined velocity. Now, when I look at what we know here, we know both masses, but we don't know either velocity, which means although I can create this conservation of momentum equation, I can't solve it. So I move on to the next part and see if I can solve the next part. The next part has to do with conservation of energy. I have all kinetic energy right here. And if it comes to rest, I have all gravitational potential energy right here. Now this, I can set up an equation for as well. The kinetic energy here will be 1/2 the mass of the bullet plus the mass of the block times their velocity squared, which I don't know. On the other hand, that has to be equal to the mass of the bullet plus the mass of the block times G times H. I don't know H. I do know G. But I know the angle. Bless you. Can we figure out the height from the angle? Yeah, you guys better have this memorized. If you don't, I'm a little disappointed that the height is L times 1 minus cosine theta. If you have not committed that to memory yet, well, we're wasting our time then. You need to commit that to memory, because this is the kind of problem where it shows up, and this will save you a ton of time. Now, at this moment, I don't feel too compelled to work this problem. If you would like to work the math on it, I will. Raise your hand if you would feel better if we work the math on it. Okay. Then I'll help you work the math on it. You need to be Johnny on the spot with your calculators, though, because I'm not going to be able to do the math in my head like I did the last time. Clearly, I failed at that, so I don't want to look a fool again. So, looking at the right side of this, I'm going to get, I don't know if you guys realize this, we can leave it all in grams. Since we have grams on both sides of the equation, there's nothing squared or anything about it, I can just leave it all in grams. I don't encourage you to do that unless you really know what you're doing. But I do know what I'm doing. So the masses cancel anyways. So I don't need to worry about the mass here. The left side is going to be 1/2 v squared. And the right side is going to be 10 times 1.5 times 1 minus cosine 30. Right? The mass is, like I said, mass canceled out. Now, I'm going to make the broad assumption that you guys can do this. But I make those assumptions all the time and get disappointed. Square root of what? 30 times 1 minus cosine 30? And Jake, what is that?
The velocity.
That'd be great.
I got 2 meters per second.
2 meters per second?
Yeah.
I'm okay with it. It's fast, but we all okay with that? No one else seems to agree.
That's what I got when I did
All right, 3 people agree, so we're going 2 meters per second. Excellent. So now that we have the velocity, we can work the problem backwards. Ava pitched a fit when I suggested that we just not convert the masses over, so I'm going to have to, I guess, downshift and say this is 0.02 plus 0.5 times 2. That will make Ava feel better. But the right side of this is just going to be 0.02 times V initial. But you'll get the same answer if you had 500 plus 20 equals 20 times VI. But that's okay. We're all friends here. So solving for VI, I'll get, let's see, that's 0.52 times 2 divided by 0.02. So VI is 52 or 500. I'm sorry, 520? 2 divided by 0.02 is 100, right? So 0.52 times 100 has got to be 52 meters per second. Yeah, that's what it's got to be. Yeah, I'm going 52 meters per second. If I'm wrong, call me out. That way I can get 2 mistakes in one day. All right. Now, this is what you guys have to be able to do. This is the kind of problem I expect on your test. Now, look closely at what I'm going to say here. Everything on this side, you're supposed to be proficient at. If you're not, that's on you. Go practice. Everything on this side, I'll say is new. But it's not really, is it? This was AP Physics 1 work. Now, if you didn't have AP Physics 1 last year, yeah, it's new to you. You need to catch your game up. But is there really a lot happening in these collision questions? Which brings us to the final example. The final example is mathematically hard. So let's be very clear about elastic collisions. I don't want to make this about the math. I want to make this about the problem. Elastic collisions, by definition, conserve momentum and kinetic energy. So in an elastic collision, you get 2 equations. So let's say I have a, 5 kilogram and 15 kilogram object. The 5 kilogram object has a velocity of 10 meters per second. And it strikes and collides elastically, producing, some velocity. We'll say this is V2 and this is V1. This is the setup of an elastic collision. Now, a couple of points to make about elastic collisions. First, they are mathematically tedious, which makes them ill-suited for FRQs on the exam. Meaning, the reason why we have these problems is because they do exist in nature, but only at the atomic level. But the reason test writers like these problems is because they don't have to work so hard. We know from what we talked about earlier that in a standard collision, I would be unable to tell you what the 2 velocities are because we only generate one relationship. But if I tell you it's elastic, well then immediately I get another relationship that I can use to figure out the velocities. The problem is that it creates another relationship that isn't easy to solve. Both velocities are squared now. It's not the same relationship. I've got 2 equations and 2 unknowns. But in the second relationship, both velocities are squared. These are tough. They require algebra. Now, let me tell you, you solve this for one and plug it in the other is what you do. But it's more common to be asked if a collision is elastic than it is elastic and find the velocities. All right.